Hello and welcome to this recorded e-learning on power estimation. My name is Frank Nelson. I'll be your instructor for this module. This module introduces Xilinx's power estimation capabilities. This module introduces some of the primary concepts that impact the quality of results a designer will get when planning for their FPGA's power consumption. This module also provides some recommendations about managing an FPGA's power consumption. If you are an experienced ASIC designer or new to FPGA design, this module will help you reduce your learning curve and get productive and anticipate your FPGA's power consumption sooner in the design cycle. The design practices and utilities we're going to discuss are designed to promote fast and efficient FPGA design construction with as little debugging as possible. Use of the power estimation tools and the recommendations for managing your FPGA's power consumption should give you more confidence about your ability to build a successful FPGA design. After completing this module, you should be able to list the three phases of the design cycle where power calculations can be performed. You should also be able to estimate power consumption by using the X-Power Estimator spreadsheet. And you should also be able to estimate your power consumption by using the X-Power software utility after you have built your design. Some customers are disappointed with their design results if they're building a system that is sensitive to power consumption. This module is going to show you how to use the primary utilities that Xilinx provides for power estimation. These utilities support for all Xilinx devices, including all of their FPGAs and CPLDs. Keep in mind that if you have power problems, there are still many possible solutions to the problem, including the addition of heat sinks, adding airflow, choosing a ceramic over a plastic package, etc. But our goal here is to give you the tools that will help you estimate your system's power consumption so you can anticipate any problems you might have as early in the design flow as possible. As you probably already know, as FPGAs get larger and faster, the power consumption goes up. This requires FPGA manufacturers to support higher performance and larger power requirements. This also has required designers and manufacturers alike to have package power limit concerns. The first generation of FPGAs was relatively small in size and slow in performance as compared to now. Power consumption was rarely exceeding the operating envelope of commonly available packages. However, given the density and performance levels of the new generation of FPGA devices, power consumption issues can no longer be ignored. Selecting the correct package, in particular, the ability to dissipate heat efficiently away from the silicon, is now also an important design issue. The Vertex family of FPGAs have gone one step further by incorporating thermal management on chip, allowing for active monitoring of the silicon via dedicated input pins. This is accomplished with the System Monitor block and is described in the Vertex 6 user guide. To get optimum speed, device utilization, and minimal power, customers need to plan on targeting as much of the FPGA's dedicated hardware resources as possible. This means that users not only have to plan on instantiating the proper resources, but sometimes have to look for creative ways in which to use the dedicated resources. For example, most customers would think to build a FIFO with a block RAM, but most would not consider building a finite state machine with block RAM. Very often, customers choose a device that has some dedicated resources left over. So to get the most out of the FPGA, users have to very often pack the most into the FPGA for the same benefit of trying to reduce their power consumption. As you know, higher density devices require more power, and this leads to higher junction temperatures. Package thermal limits exist for all Xilinx devices, and it is important for you to anticipate your FPGA's junction temperature as early as possible. This is especially important since you will probably have to choose a package for your device early in the design flow, and changing this package can be very costly. To help you with this, you can use either the Xilinx Power Estimator spreadsheet or use the X-Power Analyzer. The spreadsheet is the earliest possible form of power estimation, since it only requires you to have a rough estimate of your device utilization and an estimate of your activity rates. The X-Power Analyzer will require you to have already built, synthesized, and implemented your design for power estimation to occur. But the X-Power Analyzer estimate will be a more accurate estimate than that available from the estimator spreadsheet. And as you know, estimating your FPGA's junction temperature will determine whether you can choose a less expensive packaging option. But this choice will also determine if your design can run at your system performance objectives, design density, use the package options you want, and of course operate reliably. Estimating power consumption is a complex calculation. It has two factors: quiescent power, which is static power used to turn on the device, and dynamic power, which is dependent on the switching frequency design activity, that is the percentage of toggle rate, and is different for each resource in the FPGA. Taking both the static and dynamic power consumption for each individual resource in the FPGA together suddenly makes power estimation a daunting challenge. This is why the Power Estimator spreadsheet and XPower Analyzer are so helpful, because they are so detailed about the overall FPGA's power consumption. Power calculations can be performed at three distinct phases of the design cycle. At the concept phase, a rough estimate of the power can be calculated based on estimates of logic capacity and an estimate of activity rates. This is done with the Xilinx Power Estimator spreadsheet. It can also be done during the design phase. In this case, power can be calculated more accurately based on detailed information about how the design is implemented in the FPGA. And this is of course done because the design has been coded, synthesized, and even completely placed and routed or implemented with the ISE tools. Thus, all of the logic resources that are actually going to be used to construct your design, including the routing, clocking, and dedicated hardware resources, are all known. And this estimate is done with the XPower Analyzer. Lastly, during the system integration phase, power is calculated in a lab environment using the actual instrumentation. Of course, that's really the final say on your power consumption. But accurate power calculation at an early stage in the design cycle will result in fewer problems later. Well, as I mentioned earlier, activity rates are important for making your estimate as accurate as possible, and are also the toughest for you to estimate on your own. You'll have to estimate your own activity rates for each element in your design. This may seem difficult, but you can assign a default activity rate, which is what most people do. But the more time you spend estimating the activity rates, especially for your high power consuming components, the more accurate your estimate will be. While clocks and inputs have an absolute frequency associated with them, synchronous nets and logic will need an activity rate associated with them as well. An activity rate is a percentage of the time on each clock edge you expect the component to toggle. That means if you expect it to toggle on every clock, like the least significant bit of a counter, then its activity rate will be about 100%. Likewise, the most significant bit of a 16-bit counter won't toggle much at all and can be ignored. Now, this will vary by design, but only you know your design well enough to estimate your system activity rates. Just don't ignore the activity rates and only work with the default activity rates. Try to spend some time estimating your activity rates at least on a component basis. That way your estimate is as accurate as it possibly can be.